Right, one more extra effort to solve this integration, this backwater integration, this time using the Euler method. We used the direct step method twice with two different averagings. Now we're just going to use the Euler method. Okay, let's move down to a fresh piece of a Excel sheet. Just to get started, I'm just going to copy these this first few rows of that first method we did. Of course, these are wrong, but I can just replace those with the y naughts and drag that down, and the dy 0.3. It's showing 0.3, but that's because it's only in one decimal. Remember, 3 decimal places to the millimeter. Now, we're not doing averages in the first order Euler method. We're going just delete that whole coloured cell. We're going to delete that average because we're going to use the value at the beginning of the integration. So we're going to start with 0. Y at the beginning is 5, and we just calculate our A, P, R, crowd numbers, etc., all using the same formulae that we did before. So using the Y and the B, using the Y and the B as well for P, getting the R, crowd number 1 minus crowd number squared, etc. Same calculation. Tidy that border up. And dx is simply this equation. Let's put that next to where we're doing that calculation. But actually, we're not using the mean value. We're going to use the current value. So, pen, I'm going to cross off that mean. We're going to use I, the current value. Current. Okay. So we're calculating FR at YI or Y naught in this first case, and SF at Y naught. So it's a bit simpler. Well, it's considerably simpler. I'll stop inking that. So the delta X is now dy, I need an F4 there, times 1 minus FR slash FR squared slash S0 minus SF. Okay, I'm going to change that display of the numbers from scientific to general and have it as 1 decimal place. Yep, but that's meters. Okay, so 308 meters as opposed to 312 in the previous one, and the first one 312.5. So it's a bit different, not quite the same. Let's do the fill the table. Now, why this one might be preferable is to do any calculation is because it's much easier. The first thing we have to do is just copy down that's not right again. That should be the one above plus the dx always. First thing we do is copy down the second row. Right, looks like we've got a mistake. Why have we got a mistake? We've got that y is wrong. That should be plus. And this time again it's dy because we're at the next the next y value. Okay, so we've got this second row, and all we do now is drag it down. More mistakes. Okay, where's the mistake here? Yep, that should of course been F4. So if I just drag that down to the bottom, that should probably work. Yep, that's all working. But we're one row short, so that's 10 meters. So at y0 of 2.4, and again, correct your decimal places. We're doing 3 for y to get it to the millimeter. At normal depth, it's taken, this is the solution, 4,706, so 4.7 kilometers, whereas that was 5.84 kilometers. Which is most accurate? Well, you would take this first direct step method to be most accurate, because that's slightly higher than first order, and this Euler method is definitely first order. We should just note that that last line is not necessary because we use that dx. Okay, so there's the Euler method, the simplest method. Or maybe we want to check how the Euler method might be if we had smaller steps, smaller space steps, and I'm just going to do that for the Euler method and see how the solution changes. Let's just note this down now. Excellent. So we've got a 4,000 dx equals, so x to the x to normal depth will be minus 4,706 meters, right? Now I'm going to half the space step, the dy. Yep. So we put in, I'll just divide that by 2. Yeah. Now we've got to 3.7. We're going to have to increase this a bit. So we are going to need that row. And I'm going to increase this until we get in, so for another 10, but it's until we get to 2.44, the normal depth, which is there, right, 20 steps. And that's, remember, that line's not included. What we see here is that we've got an x equals minus 5,280 meters. We compare that to the first Euler method. The first direct step method, which is 5,854. Now, what you should really do when you're doing numerical methods is do comparisons until your numbers don't change. Let's just do one more step, see if it makes any difference for the Euler method for one more step, right? Let's change the y even smaller, so half it again, so a quarter. Right. So we're going to have to have 40 iterations to get down to 2 normal depth. So there we go, right, 40, that's it, the others are irrelevant. Cancel that. And what do we get? We get x equals minus 5,850 meters, as opposed to 5,280 or 4,706. So the interesting thing to see is that this one is going much closer to the first direct step method, which was 5,854. What we should really do is a direct step method increasing the reducing the space step, sorry, to get higher accuracy, and see which one that converges to. I may do that on a separate video, but this example here was to show you an implementation of the Euler method for doing the integration. By far the easiest, probably, well, numerically it's definitely the least accurate, but definitely the easiest to implement. So if you're going to do one of these methods, I think this direct step method with the averagings of y, you should attempt first, if that is possible. Remember, this is only possible if you're doing a delta y step and you want to calculate delta x. It's not possible if you don't have the delta y. You would have to resort to an Euler method and reducing the steps, the step size. Okay, thank you.